Here we go. Hello and welcome to the Daily Space for Thursday, August 16 of 2018. I am your host, Dr. Andres Plazas, and as always, we're going to bring you a roundup of today's news from space and astronomy. So, our first story for today, there you go, comes again from the Goldschmidt conference, like one of the stories that we talked about yesterday. So, this conference is happening right now in Boston. It's an international conference in geochemistry and is hosted jointly by the Geochemical Society and the European Association of Geochemistry. And in this study that we're going to talk about today, the scientists have found that what they call that the Earth's building blocks seem to be built from pretty normal ingredients. So that is to say, pretty common ingredients. So scientists have measured the composition of 18 different planetary systems that are up to about 500 light years away, and they have compared these compositions with the composition of our own planet. And they have found that many elements are present in similar proportions to those found here on Earth. So the backing up a little bit, so we know that the first planets orbiting other stars or exoplanets were found in the 90s, about in 92. And since then, scientists have been trying to understand whether some of these stars and planets and planetary systems are similar to our own solar system. So in general, it is difficult to examine these bodies directly because, of course, they're very far away. There are huge distances involved, and the star that is close to one of these planets tends to draw out any electromagnetic signal that could come from the system. For example, light or radio waves. So sometimes we need to start to explore our different methods. So for this particular story, and because of this, the team of scientists decided to look at the planetary building blocks, how they are affected by when they are in the presence of a white star, or when they are in the vicinity of a white dwarf star. So these are stars that have burned off most of their hydrogen and helium, and they are very dense. They have shrunk to a very small space, and they are very dense. And for example, we think that our sun will become a white dwarf in about 5 billion years or so. So in this study, the researchers point out that the white dwarf's atmospheres, they are composed of either hydrogen or helium, and this fact tells them this is good because it gives them a pretty clear and clean spectroscopic signal. Then they point out that as the star cools, it begins to pull in material from the planets or asteroids or comets in the system that were part of a system that was by the star, things that had been orbiting it, and in some cases then you get to form a dust disk, more or less like the rings of Saturn, you can think of it. And then as the material approaches the star, then it changes the way we perceive the star or how we see the star. So you can measure this change because it influences the star's spectroscopic signal that, to begin with, we know that it should be very clean and composed only of two elements, and allows us to identify the type and even the quantity of the materials that are surrounding the white dwarf. So the team took measurements using spectrographs on the Keck telescopes in Hawaii, and at the same time they used images from the Hubble Space Telescope. And they have been able to measure traces of calcium, magnesium, and silicon in most of the stars, and most of these white stars, and a few more other elements in other stars, even water. So even previously they were able to identify in a system that is about 170 light years away in the constellation of Bootes. They have found a system that is rich in carbon, nitrogen, and even water which is a composition even similar to what you find in Halley's Comet here in our own system. Or in general, the composition of these systems look very similar to the bulk of the Earth. So of course this would mean that the chemical elements or the building blocks of the Earth are common in other planetary systems. And then they conclude that from what they can see in terms of the presence and proportion of these elements, we are pretty normal, like very average, so to speak, which is consistent with the cosmological principle that we are not at any particularly special location in the universe. Um, so yeah, this is the first story of the day regarding exoplanets. And there's also another interesting story in the same vein, along the same vein, but this one has to do with the atmosphere of ultra-hot Jupiters. So in this second story of the day, um, sci- well, scientists have studied a different type of exoplanet that they call ultra hot. So in general, exoplanets, that are planets that are in other solar systems, of course, they can orbit very close to their host star. But then if this host star is very, very hot, like much hotter than our own sun, then the exoplanet itself becomes as hot or could become as hot as the star. So then people have coined this term of ultra hot planet. And one of these planets was discovered last year by astronomers from the United States. And in the study that we're talking about today, a team of researchers from the University of Geneva and from the University of Bern, using a combination of theoretical predictions and observations, have discovered the presence of iron and titanium vapors in the atmosphere of this type of planet, of this ultra hot planet. So the detection of these heavy metals was made possible by the surface temperature of this planet, which is of about more than 4,000 degrees. So the name of this star, of the star that they looked at in which exoplanet is hosted, is called KELT 9, KELT dash 9, and it's a star located about 650 light years away from the Earth in the constellation of the Swan, or Cygnus. The star itself has a temperature of about 10,000 degrees, which is about twice as hot as the Sun, more or less. And the star is named KELT 9b, you know, after the star, and then you just start adding the letters B, C, like in the TRAPPIST system. You have TRAPPIST B, C, and so on and so forth. And then this planet is about 30 times closer than the Earth's distance from the Sun. And due to this proximity, as I said, and due to the high temperature, then the star gets to get, I'm sorry, the planet itself gets to be very hot, as I said, about 4,000 degrees. Not as hot as the sun, but hotter even than many stars. So people then didn't know what, there was one question, like, about what the atmosphere of a planet like this would look like, and how it could evolve under such conditions. So the researchers from the University of Bern, from the theoretical side, they performed simulations on the on what we could expect to find in a planet such as KELT 9b. And then the results of the simulations showed that most of the molecules found there should be in atomic form and not in molecular form, because the bonds that hold them together are broken by collisions between the particles that occur at these very high temperatures. And the theoretical study, also predicted that it should be possible to observe atomic iron in the gaseous form, in the gas form, in the planet's atmosphere, and that we should be able to identify or to find evidence using the current technology with our telescopes. Then the other team from the University of Geneva actually used the transit method when the planet was passing in front of the hot star, And during this method, then a tiny fraction of the light from the star that gets filtered through the planet's atmosphere, and then analysis of this filtered light can tell us from the experimental point of view about the chemical composition of the atmosphere of the planets. And then for this you use an spectrograph, which is like a prism, as we have said in the past. It's an instrument that spreads white light into its components or colors. And then we should be able to figure out if within the components of the atmosphere you could find vapors of iron or the titanium, which is actually what they found. So one cool thing about the study is that the experimentalists point out that with the theoretical predictions in hand, it was just like following a treasure map, they said. And this is the importance of the interplay between theoretical predictions and experimentation. And throughout the history of physics and astronomy, you find a lot of examples when there is a dynamic exchange between theory and experiment. And as I repeat over and over again here in the daily space, in the end, of course, the final judge is nature and experiments, but it's always great to have a theoretical model that guides your experiments, and then with your numbers in hand that you can go back to your theory and then refine. So yeah, so this is so in the end they were able to detect the signature of titanium and the signature of iron vapor. And this is a discovery that reveals and tells us more about the atmospheric properties of this type of object that now they're calling the ultra-hot Jupiters. Scientists believe that in general many exoplanets should have evaporated in an environment similar to what this planet is, to where this planet is where Kelt 9b is. This is a planet that is probably massive enough to withstand the total evaporation, but this is again a study that demonstrates, so this is kind of an exception, they say, but this is a study that demonstrates the strong impact of stellar radiation on the composition of the atmosphere of a planet, as one would expect. And indeed, as predicted by the theory, these observations confirm that the high temperatures reigning on this planet would break apart most of the molecules, even including those containing iron and titanium, and then they would be expected to be found in atomic form, in form of these gaseous oxides. So yeah, that's that second story of the day that I wanted to talk about. And then the final story that I just read very recently has to do with galaxies hidden in plain sight, actually. Let me just center a little bit the image that you can see on your screen, and then basically you're looking at a quasar on the left, and then in this study the cool thing is that what people thought was just a point source of light, like a quasar, actually was hiding a cluster of galaxies. So this is a study performed by scientists from MIT, and they have found this new galaxy cluster hiding in plain sight, as they call. So this is a cluster that is at about 2.4 billion light years from the Earth, and it's made up of hundreds of individual galaxies that is surrounding an extremely active supermassive black hole, or in this case we can call it a quasar. So this central quasar is very, very bright, and it's so bright, as I was saying, that for decades astronomers observing it in the night sky, they just assumed that the quasar was right there, while alone it was just a point source. But then in this analysis, the researchers were able to find out that there are about hundreds of individual galaxies in this cluster, which is about as massive as about 700 trillion times the mass of our sun. And just to give a comparison, our own Milky Way is about 400 billion solar masses compared to this 700 trillion solar masses galaxy cluster. And yeah, of course, it's a cluster of galaxies, gonna be way heavier. And so the team have also calculated that this quasar at the center of the cluster is about 46 billion times brighter than the sun. And the extreme luminosity of this quasar, they think, is likely the result of an immense amount of material or a disk that is swirling around the quasar. And yeah, so the colleagues, I'm sorry, the researchers of this experiment, they say that this might not be the only object that they could find. So they actually did an experiment. Maybe not an experiment. They created a project and they went back to analyze archival data. And they set up a survey actually called Clusters Hiding in Plain Sight, or CHIPS. And it was designed to reevaluate X-ray images taken in the past. So they started taking using archival data, analyzing point sources or objects that were very, very bright in the sky. And they were actually looking for point sources inside like a fluffy thing or a diffuse signal that came from the interstellar gas in a galaxy cluster. The X-ray fluffy signal coming from the intergalactic gas. I'm sorry, the intergalactic medium of a galaxy cluster. So in the end, they found out that about 90% of these sources that they looked at, that they revisited, they turned out not to be clusters, but they did find that the small number of things that they're finding, they're like exceptions to the rule. And yes, one of the results of this survey is actually what they presented in this press release, in this paper. So then they they comment a little bit about the consequences of their study, and then they say that if this survey can find out enough of this, then we will be able to pinpoint the specific rate of accretion onto the black holes, and where it switches from generating primarily radiation to generating mechanical energy, or which are the two primary forms of energy output from a black hole. But in addition of telling us more about the mechanisms of feeding in a black hole or the accretion behavior, the detection of more galaxy clusters is of course relevant for cosmology, and it can tell us about the nature of dark energy, or in more general about the rates of expansion of the universe. Because from the theoretical point of view, you can get a distribution, a theory, a prediction of the number of galaxy clusters per unit distance or per unit volume, and more technically per unit redshift and per unit volume that you should find in a universe under a particular cosmological model. So just by counting the number of clusters or the distribution of clusters and their masses, what is called the mass function of the clusters, then you can compare that to a particular cosmological model that tells you about the different components of the universe. So just to put things a little bit in context, in the past we have talked about the accelerated expansion of the universe, how it is one of the biggest mysteries that we face right now. And we call that dark energy, and we don't know what dark energy is. And there are several methods, in particular the 4 standard methods, that tells us a little bit more about dark energy. One of them is gravitational lensing. The other one is looking at supernovae. And then there's a third one, which is counting the number of clusters, of galaxy clusters in the universe. And a study like this can help us map in a better way or the actual distribution of galaxy clusters in the universe. And just for completeness, the fourth method is called the variant acoustic oscillations, and I'm not gonna go into details, but it has to do with oscillations of the coupled plasma between the photons and the dark matter before the time of the creation of the cosmic microwave radiation. And then you can see an imprint of these oscillations in the large scale distribution of the universe. And that can also tell us more about dark energy. So on that note, on a cosmology note, we finished the stories from today, and I think we have, of course, some time to for your comments and questions. So, as usual, let's check. Oops, sorry. Let's look at the galaxies. I like the galaxies. Let's look at. I'm gonna look at the chat and say hi to everyone, and then we can talk a little bit about today's stories. Ta-da, hello. And actually looking at the chat from yesterday, from Matt's stream, and see if it's variables. Hello, 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 hello. Okay, I found it. Hello, Paranor, Susie, DPI. Hello, Larry, Tom, Astro, YYZ. Chemist and geologist doing astronomy, don't tell Shandell Cooper. That's true. Hello, Liam. Hello, Fenring. Hello, Guido B. Hello, everyone. If the star, so Hani's asking, if the star used to be bigger, why is stuff falling in? Shouldn't everything be flying away due to less gravity? Yeah, that's a good question. I don't know exactly what is the mechanism for the actually debris to fall into the star. So they mentioned in the press release that after the star has gone white dwarf, then you can find this type of migration of this material of like the pieces of what remained from whatever planet or comets or whatever was there in that system. And I don't know the exact mechanism of migration from the outer parts of the system to the closer to the white star. Yes, I will have to check that. That's a good question. I was asking myself that question actually when I was reading the newspaper, but maybe I can check it out later. Thank you for your questions. They're always very good. Sometimes I know, sometimes I don't know. But that's alright. That's science. It's okay to say I don't know. Then hello Adamald, Titanium. Hello. Astro asks, if there is such a large planet so close to its parent star, would we still expect to see a rocky planet there in that system too? So yeah, that depends on the conditions, on the environmental conditions, and as they point out in this story, they said that in such high conditions of high temperature, researchers think that most exoplanets would just evaporate and would just not be able to withstand this type of conditions. So it would have to be like an exception, like this ultra hot Jupiter that they found with a very large mass, and I didn't think that a rocky planet would be able to actually survive these conditions. But again, there might be exceptions, and yeah, we should be open to that. So that's what I know from that. So KELT stands for Kilo Degree Extremely Little Telescope. All right, thank you, Hani. Hani's Vorwerp. I didn't know that, so yeah, that's pretty cool. I wonder what it is. Do they have it in Chile somewhere? Ta-da. What effect would an inner planet like this have on the rest of the solar system? So from what I know from our own formation of the solar system, a migration of this type of system would like kind of send other planets away, and just try to, it would sort of like clean due to a planet this big, like this one of these ultra hot Jupiters, it would like gravitationally sort of clean its orbit in a way that you can see in our solar system, but um, then it would prevent, of course, the formation of, it would create a distortion that would prevent the formation of other planets in that same orbit. Then the question is like, what about maybe other types of asteroids or objects? Like, then we can look at the example of Jupiter, of Saturn, where um, like behind Jupiter and after Jupiter, you can find a group of asteroids called the Trojans, and well, they have all these Greek names, and there are because there are points that are shepherded by the gravity even itself of Jupiter, but they're not like as big. It's not that you find another planet in the same in the same orbit of Jupiter. So when a migration like this to go to this close to the host star, then it would definitely disturb the formation of the of planets that are in the inner solar system. Then the other question is like, okay, what about the habitable sun? And then of course you will have to calculate depending on the distance to the star and depending on the energy of the star. Maybe the habitable sun for such a hot star is actually farther from the star. That's what you would think, right? When the temperature falls enough to allow the existence of liquid water. Did they find the galaxy cluster using lensing? They found the galaxy cluster using X-rays, and that's why they went back also to look at they were looking like for a diffuse signal in the X-ray. So they thought it was just a point source, it was a quasar. But then when they look at it in the X-rays and they look at data from X-rays, they saw this like fluffy diffuse source, and then they were saying like, okay, there might be something going on here. Like that's one way of detecting galaxy clusters, right? Just looking at the X-rays emitted by the intergalactic gas. And then they got that optical image that you can see on the right part of the screen, probably with the Hubble Space Telescope, I would think. Yes, Astro YYZ found the news release. Yes, that's the one I was looking at. Larry, so did you find about the proton shell about the neutron star? Uh, no, I didn't find it. I was gonna read it, but I didn't find it. Sorry. What holds it together, gravity or the strong force, or is it a transient thing? Well, in the case of the neutron star, is I'm not that sure, but I believe there is a similar mechanism to the white dwarf that I was talking about today. And in the end, the mechanism that is holding the white dwarf together is just Pauli exclusion's principle. Is just the electron pressure, in which you have all this dense object that is being collapsed by gravity, but then at some point you have all this soup of electrons, and they actually are due to the what is called the Pauli exclusion principle. Electrons cannot occupy the same state at the same in the same they cannot be at the same place if they have the same quantum state. So this is actually preventing the star from collapsing because of these exclusion principles. Then if you find in a particular state that electrons that have already occupied them, then there is no room for putting another electron because it's not allowed by the laws of quantum mechanics. And then this electron pressure actually is preventing the a star actually from collapsing due to gravitation, unless you have a lot of mass, and then you can actually reach something that is called the Chandrasekhar limit, that if you are massive enough, then you can just keep collapsing, and then eventually you can produce a black hole. Do white dwarfs have magnetic fields? I'm not sure about that, since they are no longer doing star stuff, no movement or at least fashion. That's a good question. Yeah, I'm not sure about that. Have they ever found other planets in a system with a hot Jupiter? I think they have, and I think I read something about that. Like here, I'm a little bit speculating about what I may have read or may not. But I think they have, but I'm not sure, and that's a good question. And because, well, at first, the type of planet, exoplanets that people could find were these giant hot Jupiters, and then they found them very close to their star, and then people were very puzzled on why these Jupiters were close to the star, whereas in our solar system actually you don't find them that close to the star, and then we think that it actually there was some sort of migration that happened in our own solar system. And then regarding the discussion that we were having before, how stable would a solar system be if it already has a giant hot Jupiter? So yeah, I don't know if they actually have exactly. I think they have if they have found another planet in a solar system, or yeah, in a planetary system that already has a giant Jupiter. Yeah, not sure about that. Okay, yes, it's the electron degeneracy pressure. Thank you, Astro YYZ, for looking things up for me in real time and contributing to the discussion. Do you guys have any more comments? Any more questions? Or then we can maybe call it a day. And I think Dr. Pamela should be with us tomorrow from Vienna. I'm gonna confirm with her. Otherwise, it will be me again. But I think that she arrived safe and sound in Vienna for the International Astronomical Union meeting that happens every 3 years, I think. So we'll see how it goes. But well, thank you everyone for watching as usual. This has been the Daily Space. It's a production of CosmoQuest, created by the Astronomical Society of the Pacific. And our goal is to put science in your brain. So if you like this show, please give us a follow. And the follows are free. And if you want to sustain our efforts, please consider subscribing. Every bit also helps. And the Daily Space will be back tomorrow and every weekday at 1 p.m. Eastern, 10 a.m. Pacific, and 6 p.m. London. So tune in tomorrow to see what is new in space and astronomy. And yeah, as I said, we'll probably have Dr. Pamela Gay back. Otherwise, I'll see you guys again tomorrow. All right. Bye bye.